Mr. N here, and we're going to be talking about the sum and difference formulas for trig functions, sine, cosine, tangent. All right, now at this point, we should know how to find things like this, sine of 30, cosine of 45, tangent of 90 very quickly. They're all on our unit circle. Those all happen to be in quadrant 1. Even if it's not in quadrant 1, sine of 135, cosine of 210, tangent of 300. These are still angles that, even though they're not in quadrant 1, they are related to their bow tie angles. They have relations to the angles in quadrant 1. They're all angles on our unit circle. Now, these are all in degrees. We can also move on to radians. Find the sine of 3 pi over 4, 7 pi over 6, tangent of 5 pi over 3. All of these we should be able to do very rapidly without a calculator because we've memorized all of these angles. They all show up on the unit circle, whether they're degrees or radians. They all show up on the unit circle. So those would be quite easy and not much of a challenge. So now, here's what we're going to be doing next. Find the sine of 105 degrees without a calculator. Now, there's a couple things here. First of all, the sine of 105 degrees, try as you might, it's not on our standard unit circle. Now, some of you are like, well, we're learning at home. Why don't I just use a calculator? Well, the reason we're going to know is because the answer you get with a calculator is very different from what's known as what's called exact answer. The exact answer means there's no rounding. All right, that if it's a square root of 2, you type square root of 2. And the decimal of square root of 2 is 1.14 something, but that's not an exact answer because the decimal goes on forever. And unless you can write out every single decimal, it's not exact. You're rounding it off. So exact answers means leave radicals as radicals, leave fractions as fractions, just reduce them, but don't change 1/2 to 0.5. I mean, I guess you could because that's even, but we're trying to keep things in terms of just fractions and radicals only. And of course, you can hit sine of 105 into your calculator, and you're going to get a decimal. But that decimal goes on forever, and it's not exact. And also, if you just go online, you're going to get decimal answers. You're not really going to get exact answers. And actually, if you go to a website like Wolfram Alpha, the radical exact answer you get is going to look different than the answer we're going to get here for reasons I'll have to explain at the very end. All right. So the question is, how are you supposed to do this if it's not on your unit circle and you're not supposed to use a calculator and we want to find the exact answer? Well, here's what you do. You actually have to learn some other formulas. I have these formulas right here, and they are called the sum and difference formulas. Now, the good news is you do not have to memorize these. Even if we were in regular school, during the test, I actually would have provided you these formulas for every test from here on out, because these formulas are not really worth memorizing. There's just a lot of work. So please, even for actual tests that we do online, please use these formulas. Do not memorize them. Just refer to them, write them down, have a website open with a tab. That's right there. There's lots of versions of these. Some use alphas and omegas. I just like A's and B's because I think it's just easier to follow. But we're going to be using these formulas. They're called sum and difference formulas because A and B all represent some kind of angle. Like A could be 20 degrees and B could be 30 degrees. And then 20 plus 30 would be 50 degrees. Right? And that would be the sine of 50. Or you could subtract them, 20 minus 10, and that would get you 40 degrees if A is 20 and B is 10. That will get you 10 degrees. And then you can expand these out. Now, this does not look that helpful. It looks a little overwhelming at first. You're like, this does not look helpful. But let's just think about this for a little bit. And that's actually, let's look back at this problem. And let's think about the sine of 105 degrees. That's not on my unit circle. But let's think about what kind of numbers do show up on our unit circle. Angles like 30 degrees shows up a lot, 60 degrees shows up a lot, 45 degrees shows up, and so on and so forth, all the way around the circle. And the question is there any way I can take some of the numbers I do know and either add or subtract them? And we're looking at sine here, so we're just going to look at the top two. Is there any way I can add or subtract any of the angles I do know from my unit circle to get the number 105? And it turns out there is a way to do it. It turns out 60 plus 45 is 105. So if we're trying to find the sine of 105 degrees, that's the same thing as the sine of 60 degrees plus 45 degrees. These two things are the same, right? They are the same thing because 60 plus 45 is 105. So these two things are the same. And now this looks a lot like this top formula, where A represents the first angle I'm adding, and B represents the second angle I'm adding. All right, so what I'm going to do is I'm just going to refer to this formula. Again, you don't have to memorize it, right? And I'm going to say that the sine of A times the cosine of B plus the cosine of A times the sine of B, because that's just, I'm just copying this formula. And now, if A is 60, it's the sine of 60 degrees times, these are all being multiplied, the cosine of the B angle, which is 45 degrees, plus the cosine of the A angle, which is 60 degrees, times the sine of the B angle, which is 45 degrees. And all of these, sine of 60, cosine of 45, those are ones I do know from my unit circle. So now I'm just going to work those out. Hopefully, if I did this correctly, the sine of 60 is just root 3 over 2. Cosine of 45 is root 2 over 2, plus the cosine of 60, which turns out to be 1/2, and the sine of 45, which turns out to be root 2 over 2. Okay, so I started with the sine, I'm not done, but just finishing up reviewing. So it's a sine of 105, which is not on my unit circle, but I realized that 60 plus 45 is 105. So I changed that to sine of 60 plus 45. And I'm adding one angle plus another angle. So my first angle I add is A, my second angle is B. Now some people are like, well, what if I switch these around? It turns out it doesn't really matter. You'll still get the same thing. So it doesn't matter which one you call A and which one you call B, it'll still work out. And so all the A's turned into 60s and all the B's turned into 45s. And then I just worked them out. And now I have to multiply these two together. Now 3 over 2 plus times root 2 over 2, just multiply the inside numbers, and that's root 6. 3 times 2 is root 6, and 2 times 2 is 4. All right, so that's root 3 times root 2. You just multiply the inside numbers. 3 times 2 gets you 6, plus 1 times root 2, well, that's just root 2, over 2 times 2, and that's 4. All right, that's 2 times 2. 2 times 2, that's where these 4s came from. And I'm adding two fractions, which luckily they have a common denominator, so I just add the tops together. Now actually, these aren't, you can't add radicals, you don't get root 8 and 6 plus 2. When you're adding radicals, unless they're the same number inside, you can't add them. Multiplying, it doesn't matter if they're same or not. You can multiply them, but you can't add them. So the final answer I'm going to get is root 6 plus root 2 all over 4, and that is as far as I can go, and that is my exact answer. Now, I could hit all these in your calculator. I could hit on a calculator, root 6, get a decimal, plus root 2, get a decimal, divided by root 4, and then that would be the decimal answer, which you could easily find online, or just on your calculator. If you just hit sine of 105, it should be the same decimal you get if you hit all of this as a decimal. And if they're not the same, you may have entered it incorrectly in your calculator, which is a little easy to do. Now, also, if you search for this online, you might see different answers that have different square roots in a different order. That can also still be correct because it's not, there's other ways to get 105. There are other numbers you could add, or maybe there's two numbers you could subtract, or there's other ways to get this that would result in slightly different radicals. The crazy thing is, even if the radicals look different, if you worked out the decimal version, they would actually all be the same thing. All right, so, but this, if I'm using the sum formula, right, and these are called, they're called sum formulas for adding. So that's a sum, and that's a sum, because they're all being added. And they're difference formulas if you're subtracting two angles. That's a difference, that one's a difference, and that's a difference formula. All right, so if you're adding to two angles to get to a total, you're doing a sum formula. And if you're subtracting them, you're doing a difference formula. And since we added 60 plus 45, we use the sum formula. Now, it might be possible to subtract two angles, like perhaps 120 minus 30 gets you 105. It doesn't, but maybe there's a way to subtract them and then use a different formula. Of course, the square roots would look a little different, maybe in a different order. But if you work out the decimal version, it would still be equivalent. So sometimes there's more than one way to put them together. But I usually say go with the easiest way first. Okay, so that is example 1. Let's try, obviously, a second example. All right, so we'll move along. Right, example 2. All right, this time we're going to try to find the cosine of 15 degrees. And same thing, we're going to find the exact answer, and we're going to try to do it without using a calculator and just getting the decimal version of it. All right, so let's find the exact version of that. Now we have to kind of think about this a little bit. What two numbers from the unit circle could we add or subtract to get to 15 degrees? And we have to kind of play around a little bit, but actually if we do play a little bit, it turns out that if we do 45 minus 30, that gets us 15. So that's what I'm going to do. I'm going to change this 15 into 45 degrees minus 30 degrees. And that means I'm going to be using the difference formula. I'm going to be using this formula right here. Okay, this is my A angle, so 45 is my A angle, minus the other angle, my B angle, so 30 is my B. Okay, so I'm not sure if I'll see, yes, we can still see it, right? So that's going to be, now, according to the difference formula, I'm using this one here, I'm doing a cosine of some angle minus another angle, 45 minus 30. I use this, I do the cosine of the A angle, which in this case is 45, right, times the cosine of the B angle, so the cosine of 30. Notice the minus is separate. And this time I'm going to add the sine of the A angle, which is 45, times the sine of the B angle, which was 30. All right, so that's how I use my formula to get that. All right, so this part you just use the formula. All right, so that's my A angles, A and B, A and B. Notice the different formulas do have different combinations of sines and cosines, pluses. Turn up for sine, if you add the angles, you add them. If you subtract them. For cosine, it's the exact opposite. If you're adding angles, you subtract. If you subtract, you add. But you don't have to memorize any of that. Just refer to this sheet and just follow what it says. You don't have to really worry where these came from. It's a little complicated where these came from. Notice the tangent ones are a little messy. We'll be doing the tangent example next. All right, but just follow the formulas. You don't have to know where they came from. So if you're subtracting two angles, you subtract. If you're adding two angles, add them, okay? So now we've broken this down into angles we already know. Cosine of 45 degrees, hopefully if I did this correctly, is just root 2 over 2 times the cosine of 30, which is 1/2, plus the sine of 45, which turns out to be root 2 over 2, times the sine of 30, which is root 3 over 2. And now we just got to do some algebra and work this out. Multiply these two together, multiply the tops. So root 2 times 1 is just root 2 over 4, right? So that's that times that, right? Plus, multiply these two together, root 2 times root 3. Just like before, it's going to be root 6. If you're multiplying them, they don't need to be the same. You just multiply the numbers over 2 times 2, which is 4. So now I have root 2 over 4 plus root 6 over 4. Now these don't reduce. Don't say, oh, well, 2 over 4, that's just 1/2. Remember, this is root 2, so you can't touch these square root numbers if they're inside. So this can't reduce, and neither can this one. You just have to leave them like that. However, this fraction plus this fraction, they have a common denominator, and I can add them together. So I get root 2 plus root 6. But because I'm adding, remember, multiplying rules and adding rules are different. Multiplying, it's okay to add them, multiply together. If they're different, adding, you can't. So you just leave it like that, and common denominator 4. Again, that is my exact answer. Because adding, you can change the order. If you had root 6 plus root 2 over 4, that's the same thing. Right, so the order doesn't really matter very much on that one. And that again is your exact answer. Now, if you go online and research this, you might find some different answers because there's other ways to get the cosine of 15. There's some other formulas you can use that are a little different from these. And actually, we're going to be learning them next week. And if you use a different formula, you get a different answer. And some students are minds are boggled like this looks totally different. If you Google this online, the answer you get does not look anything like this. But if you got a calculator and did the decimal of this, and then figure out the decimal of what you see online, you would discover the two decimals are exactly the same. So there is more than one way to get these square roots to work out. Okay, so we're going to do one more example, and I think we need to do an example of the tangent. And we also need to do an example where it's not maybe just degrees, because you can also do this with our friends, the radian. All right, so I'm going to do one more example with a radian. All right, so example number 3. All right, so we're going to find the exact answer for the tangent of 5 pi over 12. And we're going to try to do it without a calculator. Okay, now the radians get a little bit trickier because if you really think about it, you're like, well, there's nothing on my unit circle in radians that has anything over 12. There's nothing over 12. So these are a little bit harder to come by, but you still have to think about your common radius. So think in your mind, what are some common ratio radians, like pi over 3, there's pi over 4, there's pi over 6, and so on. And let's think about these. If you added any of these together, they're fractions. And if you have fractions, you would need a common denominator. And what would be the common denominator of any of these fractions? If you added, like, say, pi over 4 and pi over 6 together, common denominator would be 12. Or if you had to add pi over 3 plus pi over 4, that common denominator. So a lot of these are going to be over 12 because no matter how you combine them, the denominator almost always turns out to be 12. And there's a lot of different ways you can add or subtract them. So I'll just kind of give you a hint. And the radian ones tend to be a little bit more difficult, so I do tend to give hints. But it turns out that if you take pi over 4 and add it to pi over 6, you will get 5 pi over 12. Some of you are like, I don't believe that. So let's actually try to figure that out. If we add that together, we would need a common denominator. This would be 3, and this would be 2. So you get 3 pi over 12, that's a 3 pi over 12, plus 2 pi over 12, and that sure enough is 5 pi over 12. It is the same thing, right? So I'm going to change this to tangent of pi over 4 plus pi over 6, all right? Because of this hint, I will give this hint there. I'll tend to give you the hints for the radians because they are a little trickier to come up with. They take a lot of work, so I tend to give hints. But actually on the homework, sometimes they won't give a hint. You're just going to have to experiment and kind of figure it out. Make a list and kind of just randomly add some common radians, add and subtract them, and kind of see what you get. Also, notice if you subtracted these, you would get just pi over 12. So if you want to do pi over 4 minus pi over 6, that would just be pi over 12, and you could use the difference formula, right? But we're using the sum formula. So if it turns out 5 pi over 12 is the same thing as pi over 4 plus pi over 6, as we demonstrated here. So that means I now need to go to my tangent formula, which is this one here. There's also a subtraction formula, but we're adding them together. So I'm going to use this formula right here. All right, so now this formula is a little bit messier. This is my A angle. The first number is always your A, and I'm adding to it the second angle, which is your B angle. All right, so this formula is going to turn out to be the tangent of, so it's A plus B, tangent of A, so tangent of pi over 4, plus the tangent of the B angle, right, tangent of B, which is pi over 6, all over, because it's a big fraction, 1, which is just in the formula, right, 1, minus the tangent of A, which is the same thing here, tan of pi over 4, this time though, times the tangent of B, which is pi over 6. So that's using this formula. Now I don't need this formula anymore. It can go away because I've plugged everything in. But now I have the unfortunate job of working all of this out. Right? Now luckily the tangent of pi over 4, I've worked that out. The tangent of pi over 4, this turns out to just be 1. I didn't check it out on your unit circle, but it is. Plus the tangent of pi over 6. And if I did my math correctly, I believe that turns out to be 1 over root 3. So that's the tangent of pi over 6. All over 1. That's a different one. This one came from up here. This one came from down here. Minus the tangent of pi over 4. Luckily, we already figured out the tangent of pi over 4 is just 1 times the tangent of pi over 6. That's the same thing here. 1 over root 3. So that's what I get when I figure out all those sine values. And I didn't need a calculator for any of that. I actually knew all that already from my unit circle. But now the happy part comes in where I actually have to work this out. Now I'm going to leave the top the same. So 1 plus 1 over root 3 all over. And let's work out this. Actually, luckily, 1 times anything is just 1 minus 1 over root 3. So now I just have that. But that's actually technically a complex fraction. So I need to actually work this out and get a common denominator. Now if I do, it's going to be 1 is going to multiply top and bottom by root 3 over root 3. So it's a root 3 over root 3 plus 1 over root 3. And that is going to turn out to be root 3 plus 1 all over root 3. That's just this circle, the top half of the fraction. All of that is over, it's going to be over the bottom part of this fraction, right? So same thing, I need a common denominator, root 3 over root 3. So that's going to turn out to be root 3 minus 1, root 3 over root 3 minus 1 over root 3, which turns out to be root 3 minus 1 all over root 3. So now I'm left with that lovely fraction right there. And this is looking pretty messy. This is why we studied so much in Algebra 1, right? But now I have a complex fraction. So now to take this, I take the bottom fraction, I multiply and turn it over. So it's root 3 over root 3 minus 1. I take this one and flip it over. And luckily, there's some good news. The root 3's end up canceling. So my final answer turns out to be root 3 plus 1 over root 3 minus 1. And technically, that's still not the correct answer because we have a square root in the bottom. But my point of view is we've already done so much work, I will accept that as a final answer. I even usually tend to leave my answers like that. Now, if you go online, I did research this online. This is not the answer you see online. They have a totally different answer. And I'm actually going to show you how they got that, but it's going to be optional. So if you kind of feel like you've got enough, this is probably fairly soon just a good point to stop the video. But for those of you who want to see how this can actually go further, because it actually can go a little bit further, I will do that at the end part of the video, but it'll be optional. Now, these are the only examples I'm going to do here. There's lots of videos I'm going to show you and refer to you online that give lots more examples by other people. And now that you've kind of seen my background and my approach, I think you'll kind of be able to figure out what they're doing on their approaches, okay? So if you're satisfied, if you're happy with this answer, you can just stop the video now. For those who want to figure out how this answer can work out even more, because it can work out more, let's continue and work this answer out even a little bit more. All right, so I'm going to copy it here. So this is the bonus material. This is for those of you who really want to know that this can be simplified further. Now, it's simpler. We have to get rid of this square root down here. And to do it, this minus 1 screws things up. So it's kind of just a trick. You just kind of have to know. It's kind of hard to figure out. The way to get rid of this is you have to multiply this by something called the conjugate. It's opposite, and you have to do that on the top and the bottom. This is not an intuitive step. You kind of just have to know this. The step is called the conjugate. And the conjugate means you do the same thing except you change the sign in the middle. So since it's minus 1, plus 1, and you have to do the same thing on the top and the bottom. You do the conjugate of the bottom part of the fraction because that's what I'm trying to change. Right? And now I actually have to multiply all of this together. All right, which is not fun. Right? And you don't want to well, nothing cancels. So I have to work out the top and you have to FOIL that. So when you FOIL that, right, first root 3 times root 3 is 3. Plus the inside, which is root 3, plus the outside, which is another root 3, plus 1. That's what happens when I FOIL all of that. Over, and then I FOIL this. Now, here's a tip. Root 3 times root 3 is 3. And then the middle terms are going to cancel when they're conjugates. So you don't have to worry about the inside and the outside. Negative root 3 plus root 3 is going to cancel. And then negative 1 times 1 is minus 1. And work that out, you get 3 plus 1 is 4, plus 2 root 3 all over 2, right? And then when you get that, basically, you can factor 2 out of the top, and you get 2 times 2 plus root 3 over 2. And then these 2's cancel, and the final answer you get is 2 plus root 3, which is when I went online, that's the answer I actually saw. But they just simplified this. Like I said, I am happy if you just leave that on the test, and on the Schoology test, I will probably leave things like this as the answer, because then I know if you just go online and do it, they're going to do the final answer, and I'm actually stopping before the final answer. So what you see online and the answer I'm going to have you pick are going to be different, because I want to do my work and just stop there. And I think that's good enough. So that's how I can actually, maybe I would just solve this on the test, and this will be one of the choices. And I don't think I would offer this as a choice, even though that's what you would see online. I'm kind of trying to prevent some cheating online by just Googling the final answer without seeing all the steps. So by having this as my answer choice, I know you've done actual work rather than just Googling the answer. Okay, but that's how you might see different answers from here to here, and that these two answers really are the same thing. All right, so good luck, everybody, and we'll see you later.